Okay, so I'm going to, in the two lectures I have prepared, I'm going to talk more about how actually to program the machine. So, Jim's talking about using the semantic database platform that the company has developed in order to do, search and knowledge discovery, types of things that you would do maybe at a more expressive level than, on an Oracle database. But I'm going to talk really about how to just program the machine. So if you wanted to write your own code, either in C or C++, which are the two languages supported on the machine, how would you go about doing that, and what's the right way to think about programming this machine? Because it is different than, an MPI cluster, which is the typical platform on which people write parallel programs today. So, a programming course really takes about 2 days, to go through sort of everything in detail. So obviously, I'll keep this at a fairly high level. But I wanted to, in the first lecture, present sort of just, the basic, what you really want to do if you sat down and wrote a code for the XMT, right? It's actually a very simple machine to program, but it is different than other parallel platforms. And so, you have to sort of adopt this different way of thinking. And if you do that, it's actually a very easy machine to program. And there are two basic techniques that are used. It is either, for loops. So you just want to write parallel for loops and then leave the rest to the compiler, or recursion, right? Those are the two simple ways to program the machine. And then in the second lecture, I'll cover sort of, the ability of this machine to support a wide variety of different parallel programming techniques. Obviously, recursion is one of them. This is not something that you would, you wouldn't write a recursive program to run, for example, on a cluster, just because, the spawning of tasks and the distribution of the work as the recursion progressed would cost a lot of overhead, and it's just something that you wouldn't do. But this machine supports recursion well. It also supports other parallel programming techniques, particularly dataflow techniques, which can expose lots of parallelism, keep the machine very busy, and also allow you to write very simple, elegant programs, which can save you a lot of programming costs as well. So I'll cover that in the second lecture. Okay. So just a couple of introductory slides. What is, parallel computing? It's just basically the use of multiple computing elements to solve a problem faster. And, these days we build computer platforms that have multiple systems, multiple nodes, multiple processors, and even multiple cores. The right way to look at the XMT is a system with, multiple processors. Parallel computing these days is becoming ubiquitous as power constraints limit the performance that we can get out of single chips. So, chips are no longer becoming faster, but we're putting sort of more pipelines into the same real estate, into the same space. Everyone's going to have to start writing parallel programs. And in particularly, the many-core chips or the many-core processors really provide you with a shared memory node, right? So you don't want to write an MPI program to run across, the multiple cores of an Intel x86 because the overheads will simply kill you. So shared memory programming is going to become more ubiquitous as we go forward, as it's got to be sort of the programming model that people will use, at least at the node or processor level. Then, on the large machines, which are constructed out of, tens of thousands of nodes, there may be an MPI layer at the very top. But at least within the node or within the processor, people will have to adopt, shared memory programming model. And so, this is the model supported by the XMT. So things that you learn in this class at least will be, allow you to at least program at least at the node or processor level in the large machines as well. Okay. So there's good and bad when you come to shared memory programming, right? The good is that any processor, any core, any thread can read, any data item. Okay, so if I have a shared memory view of the world, then, I don't need to do any data partitioning, and I don't have to do any message passing. I can have every thread simply read and write, what it needs. And even in the distributed memory world, this is becoming sort of, recognized as the easiest way for programmers to write parallel codes. We see these emergence of these various PGAS languages like Chapel and UPC, which provide the programmer at least a global shared memory view of the world. and then under the covers, the the runtime system and the compiler are deciding where the data resides and sending the appropriate messages. So shared memory programming, at least from the programmer's point of view, is certainly the easiest model to write in, and this is also even on the distributed memory machines is becoming sort of an adopted programming style. Now, if I have true shared memory versus sort of the PGAS languages, then I can read and write with very little overhead, so I have lower latencies for my operations, and hopefully I have larger overhead. So that's good. You don't have to worry about partitioning. You don't have to worry about task scheduling. You don't have to worry about really where things are. You simply write programs with loads and stores, and you're sort of done. The bad thing is, though, that because any thread can read and write any data item at will, you end up with race conditions, okay, where one thread tries to read a data value that another thread is writing, and they read and write in the wrong order, and so then you end up with reading the wrong values at the wrong time. And so you have race conditions when you have shared memory programming. This is something that doesn't exist in MPI, right? In MPI, each task owns its own data space. If I want to read or write an element that some other task owns, I have to send it a message. Then that task, replies with the data item. And so, there's a gatekeeper, as it would be for every data item, because tasks, own their own data. In shared memory, unfortunately, everything is opened, and so everything can be read and write. So the good news is that you don't have to worry about partitioning, message passing, and thread scheduling. You do have to worry about getting your synchronization correct so that things are read and written in the right order. So there's always good and bad. Okay, so processors have gotten faster and faster over the years. Unfortunately, the memory systems haven't kept up, and particularly the networks haven't kept up. Okay, so machines back 10, 20 years ago had much faster and much lower latency networks. The T3E, the vector machines like the C90 and the T90 had much better networks than we have today in our systems, and they could provide much better bandwidth and latency. So in some sense, the processors have gotten faster and the networks have actually gotten worse. This has created something that's known as the memory wall, and we have these tremendous latencies where a processor can execute an instruction every nanosecond or every other nanosecond, but it may take 10, even 100 clock cycles to get memory or data word from even the local memory. And since most operations need 2 words of memory, and return only one word, right? They compute a word and read 2 words. You can get 1 word from the previous instruction, but on the average, you have to always fetch some word from memory. And so, if it takes you 100 cycles to fetch that word from memory, then you're not going to execute an instruction every cycle. You're going to execute an instruction every 100 cycles, and so your utilization is going to be very low. So what modern processor manufacturers have done they've built a hierarchy of memory systems with some very close fast memory to the processor. That would be your L1 cache, and then caches that are L2 and L3, so they're a little further away, they're a little slower, they're a little cheaper. And then you have your DRAM memory, which is typically in the order of 300, 400, 500 cycles away. And of course, there they can provide you with gigabytes of memory, but it's hundreds of cycles away from the processor. The L1 caches are typically 2 to 3 cycles away, and L2 is usually in the order of 30 or 40 cycles away. So if you can construct your program so that you can break your data up into groups and have the data in the right levels of cache when you access it, you can maintain fairly high utilizations in the order of 50, 60%. LinPack, which is the typical benchmark that is used to, of course, for performance measures, is very suitable for caches, and they can block it up in the cache. And so, you'll read in a section of the array, you'll compute, lots of operations on that section of the array, flush it out, read in the next section of the array. And so, LinPack, and that's really the best you can do, typically maintains, the order of 70 and 80% of utilization. But if you're reading things out of the L2 or cache or L3 and even main memory, then you're going to lose a lot of performance. So there are two other ways to hide latencies. One is with vectors, and that's what the old vector machines used to do. So instead of reading a word of memory, computing on it, reading the next word of memory, the vector systems were able to read, starting at a memory location, they were able to read 1024 or some large number of words, and those words would flow into the processor. They would be put into vector registers, and then a vector operation would be done on the two vector registers, and then the next 64 words would flow in. So it was like a train. It would take a while for the first word to arrive, maybe a couple hundred cycles, but once that first word arrived, then every other word would arrive a cycle later. And so it may take me 1024 cycles to load in all 1024 words, plus the startup cost of a couple hundred cycles. So in 1,300 cycles, I would read 1,000 words, and so I was reading a word on average every 3 cycles. Okay, but that requires me to write a vector code, right? Something with large vector operations, and a lot of codes don't have that, and so the vector machines became their application set shrank and shrank over the years, and eventually they sort of died off like the dinosaurs. There's a third way to hide latencies, and that's with parallelism. Okay, and that's what the XMT does. Okay, so what the XMT does is it maintains lots of threads, 128 threads per pipeline. Okay. So every pipeline has 128 register sets, okay? And each of those register sets could be executing a different thread of operations, okay? A different set of instructions, all right? And what the processor does, and I have a picture of it later, is it basically switches among those register sets or among those threads to get a ready instruction, all right? So as long as one of those 128 threads has a ready instruction, then the processor will stay busy, okay? And those 128 threads could be from your code, they could be from somebody else's code, it doesn't matter. As long as one of them has a ready instruction, the pipeline will stay busy, okay? And so as a programmer, your only job really is to provide a code with a sufficient number of threads so that each processor can have 128 of those threads active and therefore always find the ready instruction to execute. Okay. So your job as a programmer is simply to write a code with language constructs that parallelize at a high degree. Okay. So for loops are an excellent place to get parallelism, right? You write a for loop. The for loop has a range from 1 to n. If n is a couple of thousand, hopefully you'll have a couple of thousand loop bodies that can execute in parallel. You'll have a couple of thousand threads. They'll get mapped to the machine. Each of the processors will have plenty of things to choose from, whenever it does a long latency read and write operation. Okay, so that's why the easiest way to program this machine is simply to write parallel for loops. Okay, so if you can construct your program as a series of for loops, each of which is parallel, you're done, right? So it's very simple. Okay, so this is sort of what the processor looks like. So this is, a conventional processor. There's a core here. It has a program counter and it has a register set associated with that core. And what happens is that some, schedulable unit of computation, some, thread, series of instructions is basically assigned to this core. And the registers are loaded up with the, the data values that instruction sequence will consume. And the programmer counter, steps down one instruction at a time, and the instructions are executed. So if a read or write operation is executed, it may take a dozen, or if it a few cycles if that data is in cache. It may take a couple hundred cycles if that data is in local memory, and it may take thousands of cycles if the instruction is actually some sort of MPI read or write. And while that data is being fetched, the program counter will stop before it can execute the next instruction, which is possibly dependent on that data value. And so, it'll basically stop there and wait for that data to arrive, and the pipeline will, stay underutilized. Now, you can obviously take advantage of instruction-level parallelism, so you may have 2 or 3 instructions which are not dependent on the read or write operation you just executed, And so the processor can stay busy for a few cycles, but typically the pipeline will stall. What the XMT has instead is a single pipeline again, but instead of one set of registers with one program counter, it has 128 register sets with 128 program counters. And those 128 program counters can be anywhere, right? They could completely different. So that's a little different than like with GPUs or SIMD type machines where you can have a lot of threads, but the program counter is always at the same place. And so if the different threads have, they're doing different work, then it's difficult to compose the program and use the GPU effectively. So let's say the processor has selected this thread here to issue an instruction or its next instruction, and that instruction is some read or write operation. So just like on any machine, that'll take 600-700 cycles to execute because there's no cache; it's all local memory. And so this thread here will have to wait, not be able to execute its next instruction until that data value is returned. But what the processor will do is simply this arrow here representing the selected thread. This will simply move to one of the other 128 threads that hopefully one of them will have an instruction that can be executed. And then that thread will issue, or that instruction will be issued and begin to move down the pipeline. Okay, so the pipeline there's not a bubble in the pipeline. Instead, the pipeline stays filled. Okay, so that's sort of the idea of how the machine works at a very high level. Okay, so if I look at this, and let's say I have a single thread represented by these red lines here, these red ticks, and this is time moving from left to right. This instruction will be executed, and then this thread will have to wait a certain amount of time until the second instruction can be executed, and again, maybe the pipeline will wait until the third instruction can be executed, et cetera. Okay, so this is the way a typical single core processor would work. Okay, so you can see that here, I've executed about 10 instructions in the time from the start here to the end of the black arrow. Okay, so my utilization is whatever this length is divided by 10. So it's not too much. But let's say instead of having a single thread assigned to this processor, I had two threads assigned to this processor, each with its own register set, so there's no overhead of switching from one thread to the other. Then after executing the first red instruction, I can execute the first green instruction, right? Okay, now I've got to wait until I can execute the second red instruction, and I have to wait a certain amount of time before I can execute the second green instruction, et cetera. But you can see that in the same time that I had executed 10 red instructions, I've now executed a total of 20 instructions. And so, I've got a higher utilization, right? I've executed more instructions in the same amount of time. But, I don't have to have only two threads. I could have three threads and, et cetera. And, with each thread that I add, I fill up more and more of the gaps, getting higher and higher utilization. Obviously, at some point, I've used up all the cycles, and adding more threads doesn't help me. Okay, so there is you want to get enough parallelism to fill the machine, but at that point you're sort of done, and getting more parallelism won't really help you because once all the cycles are used up, there's no more cycles, so there's nothing more the processors can do. Okay. And in fact, with things like recursion, where you can continually create new tasks, new threads, that can create, just simply increase your overhead without providing you with additional performance. So that's a bad thing. So, there's not a problem with that with loops, but with recursion, you do have to sort of be careful that, you don't create too much parallelism to simply create lots of overhead and without any gain. And, I'll explain some techniques there to avoid that. Okay, so certainly the simplest way to get on this machine, the simplest way to parallelize it or to write parallel programs is simply take your sequential program, which is probably some series of for loops, and simply go through those, identify the most important, the most computationally intensive of the for loops, and parallelize them sort of one at a time, okay? You may have to rewrite them a little bit, restructure them in order to get, parallel loops, but that's usually fairly easy to do. And this machine provides a significant amount of hardware support to allow you to parallelize loops that, at least on the surface, may not look parallel to you. Okay. All right, so data parallelism is a simple technique. You just sort of want to write for loops, which run over the either the elements or the your data structures. So you might have something like for all guests, do something. For all atoms in your molecular simulation, do something. For all documents in your library, for all the nodes in your graph, for all the edges in your graph, whatever. You can do two-dimensional and three-dimensional type of loops, for all elements A of ij, do something. So, this is sort of, what you want to write in order to get on this machine quickly and start running parallel programs. Okay, so here's a for loop, right? For I equals 0, less than n I plus plus, and all it does is assign C of I equal to A of I plus B of I, okay? So this is a parallel loop, right? Each of the n iterations can execute in parallel. They read different values of A and B, and they write to a different value of C. So this is, just a great loop. It's just something that you would, ideally want to write for running on the XMT. Hopefully the compiler will be able to recognize this as a parallel loop. It will parallelize it for you. It will get all the resources at runtime that you need to execute the loop. So all the implementation will be done, hopefully automatically by the runtime system for you. And, you don't have to do anything more than simply write something like this, okay? Now, Fortran was a very easy language to interpret and understand, and when we used to write Fortran programs, the compiler was able to automatically parallelize, I'd say 80 or 90% of the loops. C is more difficult for the compiler to reason about, essentially because in C, the names of arrays can, of course, point to the same memory location. There's no safety in the names, and so the compiler doesn't know that, for example, A and B and C are actually, maybe different memory locations. They could all point to the same memory location, so the compiler will, of course, be conservative in its interpretation of that, and, may decide that, we can't, in fact, parallelize the loops. The Cray XMT programming environment maintains a large number of Pragmas, which you can use to give the compiler help and hint, and I'll review some of those as well. But essentially, it's a simple fork-join model. The sequential code that may precede a for loop will be executed by a single thread. When the for loop is encountered, the compiler will insert instructions before the for loop to dynamically acquire hardware resources. Those hardware resources will be acquired. The range of the loop here from 0 to n, so there are n instances of this body. Those will be scheduled on the resources which are acquired. Those resources will then execute the iterations of the loop which they have been assigned. And then when each of those hardware resources finishes its assignment, it will kill itself. And the last resource which finishes its assignment will realize it's the last one alive, and then will continue executing the sequential code which precedes or follows the for loop, okay? And all that's done automatically for you. You don't have to do any of that yourself, okay? Okay, so, as I said, you want to write a series of for loops, and so the model here is a composition or a sequence of forks and joins. So if I have two parallel regions, so just imagine two for loops following each other, a master, let's say a master resource or master processor will execute the sequential loop, the sequential code. It'll go into execute the first for loop like I explained on the previous slide. then one of those resources will then execute the sequential code following the first for loop, and then when the second for loop is encountered, resources will be reacquired, the iterations will be executed, and then those will be killed as well. Now, obviously allocating and deallocating resources for every loop would be extra overhead. So the compiler and the runtime system do a pretty good job of sort of clustering for loops into the same parallel region so that resources are only acquired once. The for loops in that region are all executed before the resources are released. Okay. Okay. So what are the good loops? So there are three types of good loops. The first type are sort of loops with no loop carry dependence. So those are your typical parallel loops. All right, so iteration I does not depend on iteration I plus 1 or iteration I minus 1. The iterations are completely independent. And those are fairly easy to parallelize, right? On the XMT, because of the special hardware operations, the support it has, it's also possible to parallelize first-order linear recurrences. And I'll show you an example of that. And it's also very efficient to parallelize anything with a reduction operation in it. Okay. So, unlike a shared memory machine, which, like OpenMP, in which basically it's fairly easy to parallelize, parallel loops without the loop carry dependence, with your for alls or your parallel regions. First-order linear recurrences are not something that OpenMP parallelizes and something that you really don't want to parallelize on a conventional shared memory node because there's no hardware support for synchronization. OpenMP does allow you to parallelize certain reductions. If you have a scalar value such as a sum, in OpenMP you can do OpenMP reduction plus colon sum, right, or the name of the variable, and then OpenMP will parallelize those operations as well. Unfortunately, you can only use locks and critical sections in order to synchronize access to the global variable. So they're a little bit more expensive than they would be on the XMT. Something that OpenMP can't do, though, is to parallelize reductions on the elements of an array, right? So if you have an array like a force array in molecular dynamics, and you're calculating the forces on the bonds, and you're adding and subtracting the different forces on the different atoms for each of the bonds. That's not something that's easy to do in OpenMP because you can only really do reductions on scalar values. The XMT compiler will not only automatically recognize those, but if it doesn't, it's fairly easy for you to do that as well. And I have an example of that. Okay, so basically, this is sort of our palette, right? This is sort of how we want to write a program. We want to write it in terms of for loops with no loop carry dependencies, or if we have to, it's fine to write loops which are either first-order linear recurrences or which have reduction operations in them. Okay, so if you just stick to sort of these three types of loops, you'll do fine, right? You'll get good performance, good scalability on the thing, fairly easy programming model. Okay. Now, the for loops do have to have a certain, form to them in order for the compiler and for them to be parallelized. And these types of for loops are known as inductive loops. Okay, so and the basic idea here is that before the loop starts, you have to know sort of the number of iterations that you're going to, or at least be able to compute the number of iterations before you start the loop that you're going to execute. And that's because at the start of the loop, we're going to divide the iterations up among the computing resources that we acquire. Okay, so if you don't know the number of iterations that you're going to execute, then you can't do that division, right? And you may turn out to, since there's no necessarily any coordination between the threads, you may execute iterations that you don't need, you should not execute. Okay. So an inductive loop is one with a single entrance and exit. Okay, so there can be no breaks, basically, all right? If you have a break inside your loop body, then you could break and therefore not execute the later iterations. But since you've divided these iterations up a priori before you started, you have no control whether someone executes a later iteration, and of course, if the break happens before that, you'd get wrong answers. Okay, so there has to be a single entrance and single exit. It has to be controlled, so the increment has to be some linear inductive variable. Okay, so again, we have to know, how the I plus plus or the I times, plus plus 2 or whatever it is, how that increment, we have to be able to compute, what the increment is, so that we can compute the total number of iterations. Okay. And again, the exit, so the test, the third term in the for loop, which is the test on when to break out, has to be controlled by this inductive variable against an invariant. So, the reason I break, or the test on the break, can't be something that changes with each iteration as well, because then again, I wouldn't be able to compute the number of iterations to start with. Okay. So, you just sort of, oops. So, to some extent, you just have to be careful that you don't write a while loop as, in C, it's fairly easy. You can write while loops or until loops in the series as a for loop. A lot of people do that. And basically, those loops aren't going to be able to be parallelized, right? Because they'll either have, breaks or something like that. And so, the compiler is not going to be able to parallelize them. But if you write sort of the normal for loop that you typically write, with a simple, I plus plus or whatever, and then something like, I less than n, or some sort of, and or operation on constants, you'll be fine. If you have any questions or, just don't feel free to interrupt. Okay, so here are examples of a bunch of loops. So the first one is I is equal to 0 to n, I plus plus, and it simply assigns b of I to a of I plus 1. The second one, I goes from 0 to n, but it's I is equal to I times 2. Again, the same computation here, b of I is equal to a of I plus 1. Here's another one where I goes from 0 to n, I plus plus. If C of I happens to be 0, then we break, else we assign d of I equal to 1 divided by C of I, right? And in this one here, we have a nested loop, I is equal to 0 to n, j goes from 0 to a of I, and then I assign b of ij equal to C of I plus b of I. Okay, so question. Okay, which of these loops can be parallel, which of these loops are legal to be parallelized? How about number 1? How many people think that one's okay? Okay, how about number 2? Number 2 is good too, because even though it's, I is equal to I times 2, and so, it's going to go up by a factor of 2 each time, the compiler is smart enough to figure that out for n, and therefore, the number of iterations can be computed at runtime. I mean, notice that n here is not known at compile time, but it is known at runtime, and so the compiler can insert code before this for loop in order to compute the number of iterations, okay? And it does that for you automatically. Okay, how about the third loop here? Is that one good? No, that's no good because of the break, right? I mean, I don't know whether or not I can execute it the next iteration because, C of I could be 0, and therefore I would have wanted to break out of the loop. Okay. How about this one here? And notice that the I loop goes from 0 to n, but the j loop goes from 0 to a of I. So the number of iterations in the second loop, varies, right? But can we parallelize that one? Yeah, we can, because again, a of I here is a constant, right? It's not being updated. If we updated a in this loop, then we would not be able to parallelize this, right? Because again, a of I would be changing. But again, the compiler can, and the compiler in fact does, it'll insert instructions before this nest is executed. It will, sum up the values of a of I, so it will know exactly how many of those j iterations it's done, and so it will automatically parallelize this this loop for you. Yeah.
What if the array A is initialized during the completion?
Well, as long as A is not written inside this nest, then when this nest is begun, when this nest is reached in the sequential execution, the values of A of I will be known, and therefore the compiler can compute it at that point. Right. Now, notice that in C, of course, we're not really sure, the compiler won't be sure that A of I isn't actually some part of B of I, J, right? So, the compiler will not automatically parallelize this nest. You will have to insert Pragmas in order to tell the compiler that it's safe to do so, right? And if you knew that A and B, potentially pointed to the same memory location because of some aliasing in the, the former parameters, then of course, you'd have to be careful with that and not tell the compiler that it was legal to do so. But as long as, A and B point to different memory locations, then it's safe. Yeah. The first and second loop? Well, go ahead. Right. Right, that's right. So, if n was a constant, then the at compile time, we would know how big n was, okay? And so then we could decide whether or not it was even worth parallelizing, right? I mean, if n is 10, then I probably don't want to go through the overhead of acquiring resources and, blah, 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 right? Because I'm only going to do 10 iterations faster just to do it on the single thread. If n is not known at compile time, okay, or for example, in this case here, where it's slightly more complex calculation, then yeah, I'm going to execute a few instructions in order to calculate n, right, and make these decisions. But anytime I can run parallel on the machine and therefore amortize the cost of memory lookup, I'm better off, right? So yeah, I mean the dynamic allocation and deallocation of resources, costs some overhead, and but it's certainly amortized well by the extra speed up. Typically, the for loops, it's a few hundred instructions maybe to acquire the resources, start the workup. The overhead of recursion, which requires the construction of a record, which is then placed on a queue for execution. There you're looking maybe at a couple thousand instructions. So you do have to be careful that either there are enough iterations so that you divide up into large blocks, or the work per iteration is enough so that you can amortize that cost, right? Right. So if you knew that, that n was going to be some small number, okay, then you could put a pragma in, which is pound pragma MTA serial, and then the compiler won't parallelize it. Yeah. Yes. No. Okay. So I don't really have the picture here, but so in XMT speak, okay, a thread is a series of instructions. All right. So for example, let's say that this loop was scheduled one iteration per thread, right? So in that case, a thread would be a single, the execution of this single statement. So, you would read A sub I, you would read A sub I plus 1, 2 read instructions, you would do the add, you do the divide, and then you do the assignment. So the thread would compose, 5 instructions, read A sub I, add, divide, assign, right? So a thread would be those 5 instructions, right? If instead, we did a block decomposition, so a thread was assigned, let's say, 10 iterations of the loop, right? Then a thread would be, those 5 instructions duplicated 10 times, one for each of the iterations, okay? So a thread is some sequence of instructions that the compiler has, organized for you, okay? And when this loop is entered, when the loop is reached, right, hardware resources will be requested. And a hardware resource here is what in XMT speak is known as a stream. Okay, and so that's a single set of 32 registers, the instruction counter, and of course that is on some processor. Okay, so the instructions that are inserted before any for loop, the compiler will say, or the instruction will be something called stream reserve, right? So some number of streams will be requested, let's say 50, okay? Okay, so you'll be running on, let's say, 8 processors, because you'll have started your program on 8 processors. So each processor will execute a stream reserve instruction, which will request 50 streams. And each processor has 128 streams, okay? Because it has 128 register sets, 128 program counters. So the processor will request 50 streams. Each processor, each of the 8 processors will request 50 streams, okay? And, you know, they may or may not be available, right? So, you know, one processor may have 50 streams, and all 50 of those streams will be then assigned to execute this loop. Another processor may only have 10 streams available, so it will add 10 streams, okay?
So we are talking about uniform memory access.
Yeah, all the memory access is uniform, right, that's right. So it's all based on the shared memory uniform access of the machine, right? So after you execute this instruction, you know, you ask for 50 streams on the 8 processors, that's a total of 400, but maybe you only get 310 in total, okay? Okay. Yes, you should program it just as a uniform memory access machine. So you shouldn't worry about, I mean, obviously some memory modules will be closer to a processor than others because it's a 3D torus network, okay? But, and then of course the memory module which is associated with the processor is obviously even closer. So what we see is that on the memory, if you read or write a word that is on the memory module or that memory module which is actually attached to the processor, then that's about 90 cycles, okay? And then once you get into the network, depending on the number of hops you do, because it's a 3D torus, you know, it ranges from, I think, 500 or 600 cycles up to a maximum of about 1,000, okay? All right, so, you know, obviously, you know, there's a big difference between 90 and, you know, 1,000, 10 to 1. Once you get off the processor, once the local memory, you know, once you go off that local memory board, you know, there's not a big difference between 400 or 500 cycles and 1,000, right, 2 to 1. So, but the problem is that, as someone mentioned earlier, the logical addresses of your data in your program are scrambled across the machine, okay? So you really don't know where anything is, right?
Can I turn off the scrambler?
No, you can't turn off the scrambler. You cannot. Now, what we've done so we had a project at our laboratory which was looking at, you know, some improvements that we could make to the compiler and to the runtime system. And one of the things we investigated was the use of, so when you boot up the machine, you can take the memory and divide it into what's known as global memory and nearby memory, okay? So the global memory is this scrambled thing, and that's what your program, when you do a malloc, you know, that's in your stack that's created when you do a function call and things like that, that's all placed in this global memory, okay? But then there's this nearby memory. The nearby memory is not scrambled, it's continuous in its memory addresses. And it's essentially used for I/O, because the I/O comes in through the standard service nodes, and that only knows, you know, that's a conventional system, and so it only knows about continuous memory. And so it'll take the I/O that you've read in and simply lay it into that nearby memory in a continuous feed. And then the I/O library will then take that I/O and then move it to your data structure, okay, scrambling it. So there is this nearby memory at boot time that is accessible through mmap, okay, all right? And so one of the things that we developed at PNNL was basically local mallocs, okay? So, you know, we were able to write programs which had, you know, calls, right, where the user could call this local malloc get malloc local in the, in that local memory board and use it. And that's useful for anything that's thread private, right? So, we see a lot of parallel threads, especially in the graph algorithms, that will allocate, data structures in their execution. Now, those are private to a thread. They don't move. They don't get accessed by other people. So it obviously makes sense to put those in local memory or nearby memory, as opposed to scrambling them across the global machine. So, we had a number of applications where, we saw performance improvements of, 2x, right? You don't get a big performance improvement because, remember, I'm amortizing the cost of these memory references, right, with the parallelism. So even though, so typically what we see on the XMT is utilizations in the, let's say, 40% range, right, 30 to 50%. And then the other cycles are wasted because, we have to wait for memory. So, even if you were getting your data accesses quicker, you can only go from 30% to 100%. So the most you're going to see is a 3x improvement. So, is it useful? Sure. And we developed, the whole malloc, the whole memory management for that. It's a limited amount of memory, so you have to be careful not to, to oversubscribe it and things like that. So, yeah, it's useful. We have a compiler in-house that supports it. Cray's never picked it up, so it's not in the distribution copy of it. But, it's useful.
So in this sense, it's different from PGAS model,
Yes.
where you understand about global memory, where the data is stored.
Right. So PGAS, things like, the SGI UV, things like that, they give you the sense of having this global shared, this global memory system that you can access. But because the processor doesn't have really any hardware support to amortize those latencies, if you simply, design your program with no sort of understanding of where things are and what you're fetching, you're going to run pretty badly, right? So PGAS is nice, it gives you, it certainly simplifies your problem, but, in the back of your mind, you always sort of have to understand where things are or you're going to, run really badly. Okay, yeah, question? Oh, 5 minutes. Oh, okay. Yeah. Right, that's right, exactly.
There are also, traditional architectures like compilers are expressing this kind of to make them faster.
Right.
So what I'm wondering is that in order to really be effective in that sense, you want to get a style of some indirect addressing.
Right.
And can this model be applied?
Yeah. I mean, here I've just shown very simple loops that, that don't really do anything complex, right? But, you can imagine loops that are written, where B of I, reads A of C of I or something, right? And then, you're running all over memory. Yeah, right.
Very similar system.
Mm-hmm.
This is the kind of visual you're seeing. But
Right.
the kind of application to be further than examples are if person named this suspect and
Right. Right. Where'd you come up with that? Right. Oh, well, no, not necessarily. Right. Right. So it's not, okay, so, but, you don't want to necessarily stop when you find the first guy, right? You want to sort of find all the guys, right? Okay, so while it's true that, in search, you'll have a lot of conditionals. That's for sure, right? And in fact, that's the sweet spot, right? Is loops where you're doing this sort of conditional search, right? You want this and that and this and that and this and that, and if this is true, you may want to, execute some additional constraints and things like that. But you don't want to just return the first instance, right? You really want to return all the instances, and so you still have this sort of parallel, upper level where, for everybody might, for all names do something, right? Because if I only stopped at the first guy that hit it, he may be a guy, he may be the gardener, and he's not dangerous, right? So. Okay, so I got 5 minutes. Okay, so here's matrix multiplication. Simple triply nested loop. If you tried to write this in MPI or P threads or something like that, this is a lot simpler. It's simply what you would have written if you were writing a sequential loop. I've got the 2 outer iterations over the rows and columns, and then a third iteration here, which is the dot product. And once I've computed the value of sum, I assign it to C of ij, right? So it's just what you would normally write. And if I just take this code, stick it, have the compiler compile it, I come out with something like this. This is a tool called Canal, and it basically allows you to take the compiled code, and it will tell you what the compiler did with the code. What we want to see is these P's, which means that the loop has been parallelized by the compiler. This $ here means that there's a reduction in this loop, which the compiler has handled correctly. And obviously the dot product is a reduction into the scalar value of sum. And so the P is good. The blanks here means that the compiler didn't have there was nothing wrong with these loops, but you can see the SS down here, which is meaning that the compiler has sequentialized the I and the J loop because it sees some dependence on this memory access, or this write to C of ij, right? And the reason for that is that the compiler doesn't know that these rows of I don't all point to the same place, and so you could be potentially overwriting previous values with your later values. So this is sort of bad. This is sort of what you don't want to see, which is your outer loops sequential, and then your innermost loop parallel, because then you'll have first of all, you'll be, lots of overhead, and, you want your outer loops parallel and your inner loops to be, sequential. So, so the solution to this, of course, is to use Pragmas. And the Pragma that you will use, 80 or 90% of the time is simply pound Pragma MTA assert no dependence. Okay. Now, because I know that the rows of I point to different memory locations, because I set up a correct 2-dimensional array, I can simply put a Pragma before the I loop, telling the compiler that there are no dependencies on I, and a Pragma on the second for loop, telling the compiler that there are no dependencies in the J loop. And by simply adding these 2 statements, these 2 Pragmas, I've taken what I would have written for the exact same code I would have written for a sequential program, and now I compile that, and you can see that the compiler has now parallelized the I and J loop. It's actually collapsed them, so I actually have n squared parallelism, or n squared threads. It's collapsed them. It's parallelized, it has generated parallelism of the order of n squared threads. And in fact, now, it says that's enough. I don't need any more parallelism because that probably will saturate the machine. And in fact, it executes the inner dot product, sequentially per processor. Okay, so it's done exactly what you wanted it to do. You've generated a ton of threads, right? N squared. Hopefully, n is like 1,000 or whatever. You've generated 1 million threads. That'll keep the machine happy for a while. All you've done to take your sequential code to a parallel code is add 2 Pragmas. Okay, so that's pretty nice. Okay, can I do a couple more, or can we go a little long? Okay, all right. Anyway, all right. So I'll do these whatever. Yeah, this afternoon. Okay, sorry. Okay, so so hopefully that was a. Hopefully I've whetted your appetite. Okay, thank you.
Okay, now for lunch we have your here sandwich something, and we have plenty of time before next.
But when we broke for lunch, we had taken this code here, which was the matrix multiplication, and we had added the 2 Pragmas, and we got something of the right structure, which is the outer loop's parallelized and basically n squared parallelism, which is enough to keep the machine busy. And then just to further show you the type of information that you can get from the canal output, so you typically see some loops, loop 2 and 3. These correspond to the numbers out here in the left-hand column. So typically there'll be a couple loops here which the compiler has created in order to do some optimization. In this case, the loop unrolling and the blocking, which is typical in matrix multiplication. And then here's loop 4, which corresponds to the I loop, the ij collapsed loop. And then loop 5 is the innermost loop, and that's the this inner product. Okay, and this usually does a good job here of identifying the number of load operations, the number of store operations, the number of floating point operations, the total number of instructions in the inner loop, and then the number of resources that at least the compiler has requested. And because these numbers don't quite correspond to the ones if you do the count here, because the loop has been unrolled, and so that inner loop actually has more instructions than what you wrote. Now, typically, the compiler will underestimate the number of resources that it needs to request. So there's a pragma that you can add, which will force the compiler to request additional resources. On the XMT1 and on the XMT2, you basically want to request 100 streams each time because the latencies are longer than they were originally on the MTA1s. But you can insert a pragma in there and get force the compiler to ask for additional streams. That'll give you more, chances of finding an instruction that's ready to execute, and therefore give you higher utilization. But the programming model is you write a program, you compile it, you look at Canal to see if it's done all the right things. If it has, you're done. If it hasn't, then you have to go in and sort of tweak things to get the compiler to do the right thing to give you something that looks like this with the P's on the outside. Okay. So here's the interface to Canal. I'm not going to spend a lot of time on it. But you got your source code up here, and then you have those loop information at the bottom window. And you can select lines here, and then the corresponding loop, the information for that particular loop will pop up in the bottom window, and it's pretty nice. So these are sort of the typical pragmas to get the compiler, to help the compiler out. Your assert no dependence is the one you want to use the most often. It's the lightest weight one. This one will basically tell the compiler no dependence, and then the compiler will be free to do other optimizations like loop unrolling and loop fission and common subexpression hoisting and all that good stuff. The assert parallel loop is really only used as the last resort, as it turns off most of those nice optimizations. You really only need to use this if you have function calls inside of the loop, and therefore the compiler can't necessarily always look inside the function. And so, but otherwise you just want to use no dependence. Two other common ones are assert local, where you give it a variable list telling the compiler that you want local copies of the variables created. And then no alias is sort of like a restrict pragma in C, which basically tells the compiler that A and B don't point to the same memory location, and therefore it's like Fortran, and therefore you can be happy. But I think in all the programs I write, 80% of my pragmas are no dependence, and assert parallel only when I have sort of these function calls inside, and occasionally I use the no alias. But no dependence is the one that one you need. Okay, so I said that the other two types of loops that the XMT can parallelize are recurrences and reductions. So recurrences actually occur quite a bit in codes. and they look sort of like this. X of I is equal to X of I minus 1 plus Y of I. So looks like there's a loop carried dependence where the value computed on the ith iteration is a function of the value computed on the I minus first iteration. So it looks like there's a strict I to I minus 1 dependence. But in fact, there are techniques which allow you to parallelize this. They're known as recursive doubling or cyclic reduction. And the technique to parallelize this is sort of well known. And so the compiler, has been taught that reorganization of the code, and so the compiler will then go ahead and actually parallelize loops of this form, or loops which otherwise would be parallelized, parallel, except maybe it has this instruction in there somewhere. So these loops will parallelize, and if you look back here, here's an example where I goes from 1 to the number of buckets in a histogram, and so the ith bucket starts, or the number of spaces I need to leave for the elements in the ith bucket is the number of elements that I needed that were in the bucket of I minus 1 plus the count of that bucket. So this is a linear recurrence, and you can see that the Canal has marked this as an L loop, which is which stands for linear recurrence, and so this has been parallelized. Okay, so that's nice. The other thing that the XMT does well is parallelize loops with reductions. So here are 3 examples. This is a simple scalar reduction where S is simply the value of X of I times Y is being accumulated into S. So this is just a dot product. This can be easily parallelized in OpenMP too. So that's not a problem. Here's an example of a min-max. Another type of reduction is a min-max operation, where basically I'm trying to find the maximum value from the array X of I. So I would write it like this, and again, the compiler will automatically parallelize that. And a third example is something known as the first or the last of the minimum or maximum value. So I'm searching in an array both for the maximum value in this case, as well as the first occurrence of that maximum value. So I return both the maximum value and then the index location of that maximum value. And again, the compiler will automatically parallelize those types of reductions as well. Okay. So there are 3 examples. Now, this one's easily parallelized in OpenMP. These are more difficult to parallelize in OpenMP. But what the XMT does well is parallelize things of this nature. Okay. So here I have a force. This is like for molecular dynamics, right? So I have a lot of bonds in a molecular dynamics simulation, and so I want to look at all the bonds that I have in my simulation. Each bond has a head atom and a tail atom, right? It goes between 2 atoms, and then I calculate the X, Y, and Z forces of that bond. Okay, and then I need to add the forces onto the head atom and the tail atom, and so that's a series of reduction operations where I take the let's say the X field of the head atom and I add X force to it, and then the Y and the Z, and I do the same thing for the tail atom. Okay, so these are reduction operations, but I don't want to lock the whole array, because if I do that, then oops. If I lock the entire array, I'm only going to be updating one atom or a pair of atoms at any one time, and everything else that doesn't affect those 2 atoms will wait unnecessarily. So OpenMP doesn't really allow me to parallelize this, because I'd have to give it in the reduction clause. I have to say force, and that locks the whole array, right? But on the XMT, I can do that at a single word, on a single word granularity, right? So the only thing that gets locked here when I do this update operation is this this one data word force of head node of 0. And then this one will get locked and updated, okay. So the locking is at a single word level, in which case all the iterations here which don't touch the same head and tail atoms can execute simultaneously, and therefore I get a lot more parallelism, and therefore I keep the machine busy. Okay, and all that's made possible by full and empty bits. So the hardware, the memory of the machine supports a single bit called a full and empty bit per word. Okay, so per 64-bit word. And that bit can be used, can be examined in order to do these synchronized reads and loads. So a normal load or store operation, like you would just write, you know, A of I or you know, S or whatever, those execute without, and they don't look at the full and empty bit. So they simply execute normally, okay? And then you can issue these synchronized reads and write operations, and there are three types. There's read full, read if the bit is full and leave the bit full. Okay, so that allows multiple readers. You can do read if the bit is full and leave it empty, so that gives you a single reader. Okay, and then on the write operations, you can do write if the word is empty and then leave the bit full. Okay, so that gives you a single consumer. Here's your single producer, and here's your single consumer and your multiple. Single producer, multiple consumer. Okay, so you can when you, instead of doing reads and writes, you know, you can do these synchronized reads and writes, and therefore control access to single words. You know, the memory operation will be issued. If the bit is set incorrectly, it'll simply circulate in the memory system, waiting for the bit to be filled or to be correct. And when it is, then the read-or-write operation will complete. So the processor only issues a single instruction, and then it just sort of sits there and spins in the memory system, waiting for the bit to be correct. And again, you know, the processor is not waiting. The processor is hopefully executing other instructions from other threads, and so staying busy. And this is the way the compiler, the hardware supports, you know, very fine-grained synchronization, very low cost, and maximizes parallelism. Okay. So I think I'll just skip these slides because of time. So I did want to talk about recursion. It is a very nice parallel computing paradigm, easy to write recursive programs, and the XMT supports recursion in terms of future statements. So the programming model has an additional statement. It's called a future statement. When the statement is executed, the thread that encounters the future statement will create a record for the statement. The record will be placed on a queue. The thread then will skip to the end of that statement and continue to execute. At some point, some other stream will be assigned to execute the record that's on that queue. That stream will then pick it up, execute the future statement, and then, you know, terminate. And that way, you know, where I had one thread executing, one stream executing before, you know, now I have two streams executing. One, the original sequence of instructions, and one, this future statement. So it's a way to do recursion. And you just have to be sort of careful that what you recurse on, you know, there's enough work to amortize that overhead of creating the record, putting it on the queue, picking it up. And in particular, you've got to be careful to terminate perhaps recursion, you know, when there's insufficient work. So if you're doing something like a quicksort, which is usually represented as a recursive program, you know, you probably don't want to go all the way down to the leaf level where you say, you know, oh, I have a single element, so I'm done, or I have two elements and I just want to swap them, right? You probably want to cut it off at a higher level when you get to a segment of a certain size, you know, just so that you have enough work at the bottom to amortize that cost. The use is pretty simple. It looks just like an embedded function call. You know, you've got a bunch of instructions here, and then you create, you know, basically a future statement. So there's the keyword future. There's a variable here, which is known as the future variable, and that's where the result will be returned. There's a set of formal actual parameters. Sorry. So this is like, you know, void, name of the function, and then the parameter list, right? Open brackets, you know, whatever statements you want to put in here. There's a return statement, which terminates the future statement and then returns the value in this name. So it looks just like a function call, you know, embedded function call. So let's see. The arguments are passed by value, so these are all copied, and the this record representing this future statement will be placed on this queue, and then they'll be executed by other streams. So an example of that is, here's a simple tree search. Okay, so I just want to search a tree and count the number of node values that match some target, right? So I declare two future variables, left and right. The $ here is just conventional. It's not necessary. It's just conventional to represent future statements with a $ so that they're easier to recognize and read. And if I'm at a root node, then there's nothing to do, so I return a 0. Otherwise, I spawn a future to look at the left subtree, and I spawn another future to look at the right subtree. So the value of this function will be returned in the name left. The value of this search tree will be returned in right. When those two trees return, those two calls return, then I set sum equal to whether or not the root node is equal to target, and then I simply add in left and right, and I'm done. Okay. So I wrote a simple recursive program, and this thing will create parallelism as it recurses. Now there's some optimizations here. So as I said before, what happens is that the main thread will execute down. It'll spawn a record for the left tree. It'll spawn a record for the right tree. Then it will come down here and it'll try to read left and right. But this read won't complete until that search tree completes. Okay. So in some sense, the thread spawns, and then sort of waits, right? So that's sort of stupid. It would be better if the thread simply spawned the left subtree and then went ahead and executed the right subtree, right? Because that way it would stay busy, right? So a better way to write this is to always declare just either the left or the right branch as the future, and then for the thread to spawn that branch and then execute the other branch itself, therefore staying busy and not sitting there and waiting for some other thread to come up to execute the right branch. Okay. There's an additional optimization. So in this case, you spawn the left branch, you execute the right branch, then you come down here, and now you wait for the left branch to finish. Of course, in some cases, the right branch may be sort of just one operation, right? It might be a very thin tree, and the left branch may be some big tree, okay, which hasn't gotten picked up yet, right? So no thread has actually gone to pick up the left branch because it's still on the queue, and you're sitting there just sort of waiting for it to return. In those cases, it would make more sense for you to go and pick up the left branch and execute it. So there's an additional function which is called touch, and a touch will inspect the variable here left. If that variable has either finished or started, it will then wait. Okay, but if it hasn't started and it's still on the queue, this will force this thread to actually pick up that record and execute it. Okay, so you're not sitting there waiting for somebody to go and pick something up. Okay, so those are just two simple optimizations that can accelerate recursive programs. Okay, so I think that's it. Yeah. Okay, so that was a quick overview of sort of the two most common ways to program the machine, which are parallel for loops and recursion. And I'll turn it over to Jim to continue on the Eureka stuff. Were there any questions or comments on any of that? I know it was pretty quick, but gave you a flavor. Okay, so I'm going to, in the two lectures I have prepared, I'm going to talk more about how actually to program the machine. So, Jim's talking about using the semantic database platform that the company has developed in order to do, search and knowledge discovery, types of things that you would do maybe at a more expressive level than, on an Oracle database. But I'm going to talk really about how to just program the machine. So if you wanted to write your own code, either in C or C++, which are the two languages supported on the machine, how would you go about doing that, and what's the right way to think about programming this machine? Because it is different than, an MPI cluster, which is the typical platform on which people write parallel programs today. So So, a programming course really takes about 2 days, to go through sort of everything in detail. So obviously, I'll keep this at a fairly high level. But I wanted to, in the first lecture, present sort of just, the basic, what you really want to do if you sat down and wrote a code for the XMT, right? It's actually a very simple machine to program, but it is different than other parallel platforms. And so, you have to sort of adopt this different way of thinking. And if you do that, it's actually a very easy machine to program. And there are two basic techniques that are used. It is either, for loops. So you just want to write parallel for loops and then leave the rest to the compiler, or recursion, right? Those are the two simple ways to program the machine. And then in the second lecture, I'll cover sort of, the ability of this machine to support a wide variety of different parallel programming 6 because the overheads will simply kill you. So shared memory programming is going to become more ubiquitous as we go forward, as it's got to be sort of the programming model that people will use, at least at the node or processor level. Then, in the large machines, which are constructed out of, tens of thousands of nodes, there may be an MPI layer at the very top, but at least within the node or within the processor, people will have to adopt, shared memory programming model. And so, this is the model supported by the XMT. So things that you learn in this class, at least, will be, allow you to at least program, at least at the node or processor level in the large machines as well. Okay. So there's good and bad when you come to shared memory programming, right? The good is that any processor, any core, any thread can read, any data item. Okay, so if I have a shared memory view of the world, then, I don't need to do any data partitioning, and I don't have to do any message passing. I can have every thread simply read and write, what it needs. And even in the distributed memory world, this is becoming sort of, recognized as the easiest way for programmers to, write parallel codes. We see these emergence of these various PGAS languages like Chapel and UPC, which provide the programmer at least a, global shared memory view of the world. And then under the covers, the runtime system and the compiler are deciding, where the data resides and sending the appropriate messages. So shared memory programming, at least from the programmer's point of view, is certainly the easiest model to write in. And techniques, obviously recursion is one of them. This is not something that you wouldn't write a recursive program to run, for example, on a cluster, just because, the spawning of tasks and the distribution of the work as the recursion progressed would cost a lot of overhead, and it's just something that you wouldn't do. But this machine supports recursion well. It also supports other parallel programming techniques, particularly data flow techniques, which can expose lots of parallelism, keep the machine very busy, and also allow you to write very simple, elegant programs, which can save you a lot of programming costs as well. So I'll cover that in the second lecture. Okay, so just a couple of introductory slides. What is parallel computing? It's just basically the use of multiple computing elements to solve a problem faster. And these days we build computer platforms that have multiple systems, multiple nodes, multiple processors, and even multiple cores. The right way to look at the XMT is a system with multiple processors. Parallel computing these days is becoming ubiquitous as power constraints limit the performance that we can get out of single chips. So, chips are no longer becoming faster, but we're putting sort of more pipelines into the same real estate, into the same space. Everyone's going to have to start writing parallel programs, and in particularly, the many-core chips or the many-core processors really provide you with a shared memory node, right? So you don't want to write an MPI program to run across, the multiple cores of an Intel x86. Always good and bad. Okay, so, processors have gotten faster and faster over the years. Unfortunately, the memory systems haven't kept up, and particularly the networks haven't kept up, okay? So, machines back 10, 20 years ago had much faster and much lower latency networks. The T3E, the vector machines like the C90 and the T90 had much better networks than we have today in our systems. And they could provide much better bandwidth and latency. So in some sense, the processors have gotten faster and the networks have actually gotten worse. This has created something that's known as the memory wall, and we have these tremendous latencies where a processor can execute an instruction every nanosecond or every other nanosecond, but it may take 10, even 100 clock cycles to get memory or data word from even the local memory. And since most operations need 2 words of memory, and return only one word, right? They compute a word and read 2 words. You can get 1 word from the previous instruction, but on the average, you have to always fetch some word from memory. And so, if it takes you 100 cycles to fetch that word from memory, then you're not going to execute an instruction every cycle. You're going to execute an instruction every 100 cycles, and so your utilization is going to be very low. So what modern processor manufacturers have done they've built a hierarchy of memory systems with some very close fast memory to the processor. That would be your L1 cache, and then caches that are L2 and L3, so they're a little further away. And this is also, even on the distributed memory machines, is becoming sort of an adopted programming style. Now, if I have true shared memory versus sort of the PGAS languages, then I can read and write with very little overhead, so I have lower latencies for my operations, and hopefully I have larger overhead. So that's good. You don't have to worry about partitioning. You don't have to worry about task scheduling. You don't have to worry about really where things are. You simply write programs with loads and stores, and you're sort of done. The bad thing is, though, that because any thread can read and write any data item at will, you end up with race conditions, okay, where one thread tries to read a data value that another thread is writing, and they read and write in the wrong order, and so then you end up with reading the wrong values at the wrong time, and so you have race conditions when you have shared memory programming. This is something that doesn't exist in MPI, right? In MPI, each task owns its own data space. If I want to read or write an element that some other task owns, I have to send it a message. Then that task, replies with the data item, and so there's a gatekeeper, as it would be for every data item, because tasks own their own data. In shared memory, unfortunately, everything is opened, and so everything can be read and write. So the good news is that you don't have to worry about partitioning, message passing, and thread scheduling. You do have to worry about getting your synchronization correct so that things are read and written in the right order. So there's always